Welcome to the Char Chit Chat, a podcast exploring all things biochar related, coming to you from a small sheep and tree farm in the deep south of New Zealand. All right, thanks, John, for joining me. I would love to ask you, who is John McDonald-Wharry?
How's it going? I'm a scientist, was lecturing to the engineers up at the University of Waikato. I came through a chemistry, biology background, undergraduate. Did my master's degree in kind of pulp and paper chemistry. So I had a big involvement with biomass material, plant products, and converting them into something useful and valuable. So did that, and that was in conjunction with Scion Forestry Research over in Rotorua. And then at the end of that, I did my PhD on a biochar project. So that finished about 2015, and I've been a member of BNNZ since its beginning.
Okay, thanks for that introduction. What do you remember about when biochar first came into your awareness? When did you very first learn about it or know about it, hear about it?
Yeah, so it would have been about 2011, thereabouts. I'd probably heard about biochar maybe a little bit in sort of media and that kind of thing. But we had, at the University of Waikato, we had a student working with Michael Antal in Hawaii. So he had been doing a lot of stuff with charcoals and biochars well before sort of biochar became popular. And my supervisor, I think, they did postdoc together with Michael Antal. So they had that connection there. So there was a thesis from one of their previous master's students. So I was writing up my master's and reading other documents created by previous students. And one of them was on the structure of charcoal and how it develops at different temperatures. And so that was quite a fascinating subject there. And I was working on pulp and paper chemistry. So a lot of the processing of wood was sort of wet processes. You use a lot of water, you're adding a lot of heat, and some of the yields from the processes that I was working on were very low. And so biochar was appealing because you get a reasonably high yield from biochar processing, and it's a reasonably straightforward process. So you're getting 20 or 30% yield, which is quite good for converting biomass into something valuable. And the sort of pyrolysis process sort of is self-sustaining and can sort of take care of itself and potentially get more energy out than you're putting in. So there's a lot of appealing things from the process side of things. And you're converting the biomass into something very different from what you started with. So that opens up a range of different applications that you couldn't use normal wood or plant material for. And from the scientific side of things, how the structure at a chemical and nanostructural level of biochar develops, especially with increasing temperature, it was quite fascinating. So I decided to do my PhD in that area.
Yeah, that sounds really interesting. So you're saying that the yields from converting a tree into paper, the yield's very low?
Depending on how you do it, I was more looking at some more of the specialized products. So the kind of applications, I was extracting some of the water-soluble carbohydrates from wood chips before making them into paper. And we were getting, I think, a few percent out of the wood chips. And it could maybe be used for kind of like a water-soluble glue paste type thing. So, yeah.
So if a stranger asks you what biochar is, what do you tell them?
I tend to go with it's effectively charcoal with different applications, and it's made from recent biomass rather than coal or sort of fossil carbon products. And biochar is often more determined by the application. So it's putting it into soil or potentially other long-term uses rather than burning it and returning that carbon to the atmosphere.
Okay, thanks for that. All right, can we go back and you talk to us more about your PhD? Try and dumb it down for us non-academics, and what exactly were you aiming to figure out? What did you figure out? And yeah, what was the whole outcome of it?
So yeah, I had three parts in there. The first part was looking at sort of more on the theory side of how the structure of biochar changes, largely dependent on what temperature you make the biochar or the char at. So of great interest there was that if you make a biochar at say 350 degrees Celsius, it's an insulator to electricity. But once you make it at temperatures above 610 degrees Celsius, so if you're making it at those higher temperatures, it becomes a conductor of electricity. So to the naked eye, they're just black lumps at both temperature. You will probably notice a more silvery look to the biochar at higher temperature, and that's related to electrons being able to move through the material. That gives it a sort of shimmery, silvery, metallic look. So that's also related to how metals are conductive. So something quite dramatic happens at about 600 degrees in the development of the biochar structure. So it's mostly carbon either side of that temperature, but the carbon itself rearranges to provide electrical conductivity, and a range of other properties change quite dramatically over that temperature range. So digging into what's happening in terms of the configuration of the atoms and the carbon structure over that temperature range was quite fascinating. From that perspective. And what I went through with that one is I took a bunch of, largely it was existing models and existing evidence, and combining them into a new or updated model for the structure of biochar when you're getting down to nanometers and atomic scale, and how that structure changes as the biochar is produced at different temperatures. And so some of that goes back to Rosalind Franklin's work. So she did the X-ray work to work out the double helix on DNA. And another thing she did before that was working for the coal board in the UK, I think, and she did some of the early work with X-rays on charcoals and coals and different temperatures. So some of the model comes back from her original work and updated with the sciences emerged since then, because we've got things like fullerenes, carbon nanotubes, graphite, graphene. So combining a number of those different features into one model to try and describe what the structure of biochar is. So that was the first part. The second part was more about quality control for biochar. So working with some of the instruments at the university to come up with a quick check for how well cooked a sample of biochar was, so how developed that nanostructure was. And I got a quick test developed. So within a minute, you could put a biochar sample in there and estimate what temperature that piece of biochar experienced during the manufacturing process, with a view to quality control down the line. So that was Raman spectroscopy, fairly expensive machine. You fire a laser at the sample and it detects a very faint infrared radiation signal coming back from the sample. And based on that, it's vibration of atoms and bonds between atoms is the simplest way to describe it. There was a view to, if you have a batch process for making biochar, is the biochar at the top of the kiln getting cooked to the same degree as the biochar at the bottom? And especially if your properties change dramatically, surface area increases with increasing temperature generally, and electrical conductivity, you've got a very different product if your bottom of your kiln is 400 degrees and the top of your kiln is 700 degrees. So I thought that would be valuable for scale up of biochar to make sure you're making a consistent product. And as part of that, I did a survey of a bunch of biochar producers, which I think we can discuss later in the interview if you're keen on that one. And then the third part was making composite materials out of biochar. And so looking more towards potential construction materials in the future. So that was sort of the application part of my thesis. And I was deliberately doing something a bit different from the agricultural and horticultural applications of biochar, which was a big research drive at that stage. So that would have been about 2012. So there was a lot of other research groups and PhD students around the world working on soil applications of biochar. So I thought that's a quite crowded space, so I'll do something different application-wise.
Yeah. Wow, so much to go and ask you about there. All right, the first thing I'm going to ask about, because I've thought about this before myself and wondered, down at the atomic level, you mentioned a couple of times that atoms are rearranging. Are they actually rearranging and moving, or are just some atoms being burnt away to leave behind a certain kind of pattern?
As you get up to 300 or 400 degrees, so if we sort of view it as you're starting at room temperature, or 10, 20 degrees or whatever, and you're heating up your material, wood chips, straw, bamboo. By the time you've hit about 300 or 400 degrees, you've removed most of the mass and weight of the material has come off as gases and tars and that kind of thing. So 70% of the mass has gone off, and hopefully you've sort of cleanly burnt that or collected some good wood vinegar or something. So most of the mass is gone by the time you get to 400 degrees. So you're left with a black solid that doesn't have a lot of surface area at that point. And then what happens from 400 degrees to 700 degrees, there's a little bit of mass loss. You get a bit of carbon and hydrogen, oxygen coming off. But over that temperature range, it's less about removing material. It's more about rearranging the material that's there. So especially when people talk about surface area, there's sort of a common misconception that it's like a block of wood and someone's drilling holes into it, removing material to create pores. Some of that comes out of the activated carbon from coal industry. They chew away at some coals with chemicals to create the porosity. But with chars and biochars, it's less about taking out the material, more about rearranging the material that's there. So the way I describe it is it's like a pile of bricks or stones at low temperature. There are gaps in there, but the gaps are too small for even atoms to get through. So it's a disorganized mess at, say, 400 degrees. So imagine it like a pile of bricks. At higher temperatures, if you get to, say, 700 degrees, it's like rearranging that bricks into an arch. So if you think of like the Colosseum or a Roman aqueduct, you've got the bricks and stones rearranged into an arch. So it's a bigger opening so people can move through that arch. So on a nanometer scale, that's sort of a reasonably good metaphor for what's going on there. So most of the lumps of carbon and sort of clusters of carbon atoms are created at 400 degrees. It's mostly carbon, but it's very disorganized. And then as you go towards 700 degrees, you get growth in graphene-like sheets and structures, and they form arch structures, which kind of push the pores open. So rather than thinking of it in terms of removing material to create a pore or a hole in the nanostructure for porosity, it's more about the graphene carbon organizing under the effect of temperature into larger graphene sheets, which push each other apart and form sort of arch structures, which provides the porosity.
Okay. Yeah.
So you've got micrometer scale porosity. So we're talking about 1,000 times smaller than a millimeter. And at that scale, so you can see this under a conventional microscope or electron microscope. So if you see those gray images floating around of biochar with all the cellular pore structure on them, I think you've got one on your podcast.
Yes.
So that electron microscope image there, that is showing the cellular structure and the porosity, and that comes from the biology structure of the plant.
Okay.
So that's at the micrometer scale. So it's usually about, say, 5 or 10 micrometers across. and different plants, softwoods versus hardwoods versus grasses versus different parts of the plants, old plants, new plants, will have differences in terms of what cells are there and the sizes.
Okay.
So that's at the micrometer scale. That will come through the whole process. So at 400 degrees, those structures will be there at that micrometer scale, and those sort of cellular structures, and that will remain 700 degrees, 1,000 degrees. You could take it up to 2,000 degrees if you had a high temperature furnace, and that structure will be preserved. It's shrunken down a bit. I think there's about 20, 30%, 40% shrinkage versus the size of the cells in the original plant material. So there's shrinkage as the material's removed, but that structure is preserved the whole way across. So if you're interested in those structures, your choice of biomass and wood is quite important. And those structures do provide water holding capacity. And that's where they talk about the coral reef for soil microbes. I think that's Kelpie Wilson's phrase that she uses quite a bit.
Mm-hmm.
So if you're thinking about the benefits of biochar in that terms, that you want to create like a habitat and niches and shelter for different soil microbes, then selecting biomass for that porosity is important.
Mm-hmm.
Most biomass will have that, but if you're doing something like wood pulp or something, or cardboard, turning that into biochar, you might not have that porosity because it's already gone through a processing step and crushed all those cells. And the other thing that people need to be aware of from that thing is grinding up the biochar too fine, because if you want to create that coral reef for soil microbes and you crush your biochar down into very fine powder, instead of that open cellular structure, you end up with basically like a pile of broken glass under the microscope. That's what it looks like. So you get sort of shards broken off that cellular structure. So that's at the micro level, micrometer level. Look at that electron microscope image on your podcast icon, and you zoom in another 1,000 times higher magnification, which you'll probably be getting to the limit of your standard scanning electron microscope, and you'd probably have to switch over to the more expensive transmission electron microscope, which is a lot more expensive and difficult piece of kit to use. You'd go down another 1,000 times more magnification, and what it will look like under a scanning electron microscope will actually be like a fairly smooth surface. But if you get onto the transmission electron microscope, you're looking at something which, metaphor-wise, it would be as if someone took a couple of rolls of chicken wire and put it through a combine harvester or something and just sort of ripped it up, tangled it up, and you've got a tangled mass of carbon atoms. And so it's that graphene type structure with the hexagonal carbon atoms, but it's been shredded, tangled, and then you've got the porosity at a nanostructural level sort of within that tangle of sheets of carbon atoms, basically. So I think that's a reasonable metaphor to get your head around about what it looks like. So we're down into nanometers level, and biochar's cooked at about 650. You've got reasonably flat sheets of carbon atoms, probably with a bit of curvature on them, about 2 nanometers, 1 or 2 nanometers across, and the porosity at a nanometer scale is at a similar scale. So you've got pores between those sort of crumpled sheets or tangled sheets at about 1 or 2 nanometers across as well. So that's what's developed at 700 degrees, and that's what gives you the sort of 200, 300 meters squared per gram surface area. So that's caused by your higher temperature treatments. So it's about 10, 20 meters squared per gram, maybe less at 300 or 400 degrees. And then once you get up to 650, 700 degrees, that's often increased to 100, 200, 300 meters squared per gram of surface area. And that's nanometer, nanostructure surface area. which is going to be too small for the microbes to live in that structure in nanometers, because microbes are micrometer size. So it's too small for them. But gas, contaminants, toxins, heavy metals, water can get into those nanometer size pores and nutrients. So that's useful for the chemistry at that scale.
Yeah.
But microbes can't get into that nanometer scale porosity, but they could benefit from that nanometer scale porosity soaking up a toxin which harms the soil microbes, or it could be a reservoir of water or air or some nutrient that, instead of leaching out of the soil, stays in that nanostructure, and the microbes may be able to extract it out for their benefit. So there's chemical benefits at that level.
Okay.
But it's too small for the biology.
The microscale is for biology and nanoscale for chemistry. I think that's an easy.
Yeah, that would be a simple distinction. Yeah.
Okay, cool.
Yeah, and they're both caused by the biology and chemistry. So microscale is caused by the biology of the plant material.
Yes.
And the nanoscale porosity is caused more by the chemistry of the carbon atoms rearranging with higher temperatures. In terms of the effect in the soil, the nanostructure porosity will be impacting chemistry a lot more. The microstructure porosity will be, at least structurally, impacting biology. It will be habitat for microbes. Yeah.
All right. Great. That's a great clarification. Do you know if your PhD thesis is freely available to people to have a look at?
No, I think it's currently embargoed because I've got sort of the composite material recipe in there. So I think it's currently embargoed. I haven't checked recently, but the first 2/3 of it have been published in papers. So some of them are publicly available and
some of them are behind paywalls.
Some of them will be behind paywalls, but if people want them, I'm allowed to send them copies. So if someone emails me,
oh really? Okay.
Yeah, send them copies of it. And I've done presentations over the years as well at different conferences. So some of those slide decks will be out on the internet. And again, if people email me, I can send those through to them.
Yeah. Okay. And your composite stuff in the third part, is that protected by Waikato University, or did you do that for another company?
No, I think I have the IP on that. I think I clarified that with the university.
What would you like to do with that IP? Would you like to sell it to a company, or is it got commercial potential, do you think? Or what happens?
Yeah, I think it's got commercial. It's got commercial potential, and I would like a New Zealand company to pick it up and start manufacturing some products. Probably start with plant pots or garden edging or something made out of it initially, and then move towards more construction type applications, because there's a lot more regulations and safety issues and things that need to be proven over a number of years before you'd want to use it in construction. But you could probably start off with kind of lower risk proving applications, but you would want years worth of proof before you started making buildings out of it or something.
Yeah.
Yeah.
Okay. All right. For the do-it-yourself person like myself, or homesteaders or anyone like that, I've done quite extensive reading on biochar, and I'm really interested in, and I've tried putting it in with cement and other materials. So like my friend builds houses out of papercrete, which is basically ground up, mashed up newspapers with cement. But I'd love to be adding char into that to add something different to it. For the backyard person, the do-it-yourself person, what kind of direction can you give them with biochar and adding it into other materials? Yeah. And why?
Yeah, so I think the why question is quite important, and that's whether you're backyard or industry or academia, why would you be adding biochar to something, and be clear about Yeah, you're not just chucking it in and hoping it's going to magically make everything better. Have a careful think about why you're doing it. So your biochar or char is probably going to be at least 4 times more expensive than your raw biomass. So that's a consideration. So that's just on the amount of mass or weight of material you lose when you pyrolyze it. So you're going to be able to get sawdust a lot cheaper than you will be able to get biochar. So that's a consideration. So wherever you're using it, it should be doing at least 4 times more value than just using wood chip as a filler. So the advantages of biochar are it's going to be a lot more stable than the woody material that you could otherwise use as a filler in concrete, whatever. So it's not going to shrink when it dries or expand when it gets wet to the same degree, which causes a lot of problems in wood composites. So the whole MDF swelling and falling apart when it gets wet. MDF board, that's the sort of key example, and a lot of biomass-based materials will do that to a greater or lesser degree. So biochar is a lot more stable to moisture, but it can also provide some of that moisture buffering capacity as well. So in Austria, I think Hans-Peter Schmidt does biochar plaster on the interior of buildings. So I think part of that is that moisture buffering capacity. So it's got that surface area, so it will help soak up the excess moisture. So there's that aspect of it. Lightweight, so reasonably low density. So if you wanted lightweight things, you can use biochar. So I think the stability is a big thing that I push with biochar, is that by turning biomass into biochar, you're ending up with a lot more stable material long term. So that's dimensional stability with moisture level. It's mechanical properties, strength and stiffness, stability with different moisture levels. You're not going to have something which softens when it gets wet. And you've also got the decay stability as well. So rotting, biodegradation. If you made your biochar at a high enough temperature, you don't have those rotting issues that you have with wood products. So I think that stability is quite important. There are other functions of biochar which different people and groups are interested in for different reasons. So there's electrical conductivity. So higher temperature biochars will have electrical conductivity, where in materials for construction and other things, that there's interest in that for electromagnetic shielding.
Yeah. I was going to ask you about that because I read about that in one of the books and I tried it. And I tried putting char into the papercrete that I told you about, made like a cardboard thickness and a flat thing. And I put it in front of electrical devices, but it didn't block. So perhaps I didn't have it at high enough temperature.
Yeah, there's a thing they call percolation threshold, where you need to have enough volume of your conductive material in your composite. So your composite, you've got your filler or your reinforcement or your active ingredient in there, and then you've got your matrix holding it together. So it might be cement, or it might be plastic or PVA glue, or whatever you're holding your material together with. You need to have that conductive filler at a high enough volume in there, so basically the particles are connected to each other, so you can get electrical conductivity. Otherwise, you've got these conductive islands sitting in the material and no way for the current to get between them easily. So you need to get that loading up high enough. And
all right. I've got one specific question for you about what we're talking about. I want to build a pizza oven. I've built many already. One of them I did cob, so that's clay, straw, and sand. And then over the top of the cob, I did papercrete, which is what I said before, paper and cement. And I did that on the outside as an insulator to keep the heat inside the cob. But what happened is that over time, after say 3 or 4 burns, when it got quite hot, it basically just turned the paper into ash and it just started crumbling off. So what I was wondering is whether just a cement and char mix, do you think that the same kind of thing would happen if the temperature inside it got really, really hot? Or because of its stability that it would, I mean, it basically needs to ignite, which would be way over hundreds of degrees, right? Do you think that would work? And what sort of percentage of char could I get away with? Because obviously I don't want to use heaps and heaps of cement. I mean, could I get away with an 80-20 mix maybe?
Yeah, you have to sort out whether that's by volume or weight. Yeah, no, I haven't actually done much, anything at all really with biochar and cement. So,
okay.
Yeah, someone like Hans-Peter Schmidt,
Mm-hmm.
looking at some of his work, and there might be other links to other people who've done biochar, cement. There's Harway, I think, in University of Singapore. He's done some work on it, but there's biochar and cement where they put a fairly low percentage of biochar, like a few percent, and it just improves like anti-fracture toughness. So it makes it more difficult for concrete type product to crack.
Mm-hmm.
That's a very low loading. But yeah, in terms of like the papercrete, so biochar, especially high temperature biochar, is going to be more thermally stable than the raw biomass or the paper or whatever you're putting in. So it won't smoke and ignite at a lower temperature. But if you raise it to a high enough temperature, your biochar, you will potentially start oxidizing it to things like carbon monoxide. So that would be something to watch. If your temperature gets high enough in your pizza oven exterior, if it's sort of glowing red coals, if it gets up to that temperature, you definitely start oxidizing your biochar and creating things like carbon monoxide, which wouldn't be good because you're losing your biochar and creating carbon monoxide. So, but it'd be about how much temperature you get on there and how much oxygen it's exposed to.
I think I'm going to try it because you don't know until you try it. I'll do some more research. What's your favorite method of making biochar? I mean, do you make some of your own yourself for your garden or for someone else's garden?
Currently, I'm using the steel bathtub method. So you get a second-hand steel bathtub, which someone's pulled out of a bathroom renovation. And that's quite good in terms of making reasonably high quality biochar in a reasonably simple way that works at sort of backyard scale or lifestyle block scale. So you can get second-hand bathtub for 30 or 50 bucks or something. And it's a flame cap method, so similar to a cone kiln, but usually a lot less expensive to get started on that. The cone kilns are pretty good. I've been impressed with those over the years. And at the end of my PhD, I actually had my quality control method and put out an open call for samples from New Zealand and around the world. And some of the cone kiln samples came in for that. In my opinion, very high quality biochars coming out of the cone kilns. There's a bit of operator skill involved in it. So I'm sure some people are making much better chars than others with the cone kiln, depending on their sort of fire management and how they're feeding them and set them up.
And the cone kiln, you're referring to the Kontiki, right, mostly?
Yeah, the Kontiki or flame cap cone kilns, yeah.
And did you get anyone sending in char from a bathtub?
No, but I think that's a bit of a more recent development. But I'd say it'd be similar if they're managing it well in terms of keeping the flame cap going and doing it for long enough to make sure that the char has seen high enough temperatures for long enough to develop that sort of nanostructure. So that's at the backyard level. When you start getting into sort of more commercial facilities, there's the whole, do you do a batch-based process where you load all your biomass into a kiln or a retort and then carbonize it as a batch? Or do you have a continuous process where an auger takes something like wood chips through various heated zones and then processes it and char comes out the back of the machine? So there's quite a bit of debate about which of those approaches is best, and depending on the circumstances, people can make good chars or bad chars with both approaches depending on how they do it, and same with emissions as well, whether it's clean burn or not. So you can make good chars with batch process or continuous process. And there are pros and cons of both sides of things. In terms of general making biochar, one of the common misconceptions is excluding the oxygen. So pyrolysis or biochar making, talk about it heating biomass while excluding oxygen. Now, if you look into it, while you're heating the biomass, excluding the oxygen isn't as important. It's more about, once you've made your char, protecting that char from attack by oxygen. So you either need to cool the char down rapidly or shield it from oxygen getting to that hot char. So quenching with water kind of does both. You're cooling it down rapidly and you're smothering it with a layer of water, which will help protect it from the oxygen. Or you can seal up a vessel on cooling, or if it's a pit burn, cover it in dirt.
And what's your opinions on, maybe backed up to some research about inoculation and charging? What would you like to say about them?
I recommend for soil applications, people, especially if they've made high temperature biochars out of nutrient poor materials such as wood chips, sort of brown biomass tends to be nutrient poor, but carbon rich. And if you make a high temperature biochar for that, I definitely recommend, if you're doing soil applications, to put it through some kind of biological process. So whether that's feeding it to animals or putting it through a composting process, maybe anaerobic digestion as well. But if it's gone through a microbial process, the microbes will potentially change the surface of the biochar. Organic acids and things attach to it and attack the surface a bit when it goes through a biological process. And these are usually nutrient-rich processes, such as composting. So you've got an opportunity for that char to soak up some of those nutrients.
Yeah.
So that's hopefully less nutrients coming out the bottom of your compost stack if you put biochar in with the ingredients at the start of the composting process. And you're hopefully getting like more nitrogen compounds taken up by the biochar and then acting as a slow release fertilizer.
Yeah. All right, John. So what are you doing in the biochar space at the moment? You're not researching anymore. You're not working at the university anymore. What's your current situation?
So currently I'm sort of a freelance consultant, doing a bit of biochar work with some companies making biochar related products. Also doing a bit of my own biochar related activity, running a few workshops, sort of at bathtub scale, community workshops. So done two or three of those at this stage. And so sort of educational biochar talks and workshops. Yeah. So composite thing I'm still interested in, but if you want to do it in New Zealand, we need to have the biochar production capacity and some companies willing to start converting that biochar into some sort of more material products.
Yeah, and how are things in the North Island? I'm more familiar with the South Island. So are there commercial producers now of quality biochar in the North Island?
Instead of large-scale biochar activity, we've had some of the old sawmills with inefficient boilers by modern standards. So your modern sawmill boiler, especially the ones coming out of Europe, will probably produce a sort of white or grey ash with basically no carbon in it because they're trying to get maximum energy return from the fuel going in. The older boilers, which a lot of New Zealand sawmills use, will produce maybe 30-50% char in the ash component. So you get a mixture of wood ash and char. So I was involved in some of the early activity about testing some of that, and then it went off. So there are people taking some of that high carbon boiler ash, usually called. And so it's basically a mixture of biochar and ash, and so some of that's going into composting processes. Now in the Waikato, we have at least 2 companies working on biochar production units, sort of shipping container or 2 shipping container size thereabouts in terms of scale.
Yeah.
So that's good to see that kind of industrial commercial activity picking up and working on different products and applications. So it's looking good in the Waikato in terms of production capacity coming online.
So is that due to come online this year or next year?
Oh, they are producing things, but there's a case of improving designs and scale up and roll out. And in the far north, there's been some biochar activity happening up there. In terms of local hapu groups and that kind of thing. So, it's definitely looking quite promising in terms of commercial and industrial activity.
Great.
In recent years.
And anything else in the rest of the island that you know about?
Bit of interest from nurseries about putting biochar in with trees. And generally awareness of biochar seems to be rising amongst councils and different organisations. So it's been a bit of a long road. Trevor, travelling around the country for BNNZ and biochar group before then, did a lot of work raising awareness in different organisations. So they don't always pick up on it immediately, but planting the seed and come back in 5 years and they've got more awareness of biochar and different applications and heard of it. So there is a definite value in doing that.
Yeah. Yeah, and I mean, you were involved quite early on. How do you see the trend? I mean, are we on the exponential curve yet, or are we kind of on a linear curve, would you say?
It's difficult to tell.
And what do you think? What do you think's needed to put us on an exponential curve?
Probably investment in production capacity.
Yeah. Yeah, it's the chicken and egg thing again, isn't it?
Yeah.
Yeah, I see the situation in New Zealand that it seems to me that you need to have a lot of money to be able to set up a biochar plant, and that you need to be able to survive financially for at least a couple of years with no income, and then maybe get your production up high enough that you can then make it financially sustainable. I'm guessing around 2 years, but it could be even longer. And we just don't have government funding. We're not really having sort of, the stock market or anything supporting it. So it's basically up to individuals that have the wealth to do it. And that's very, very slow for the industry in New Zealand, isn't it?
Yeah, there's possibly getting government funding or council funding is a bit of a double-edged sword. You may become too reliant on it and it may be fickle or that kind of thing.
Do you think New Zealand missed the boat? Do you think we should have got into commercial production 7, 8 years ago?
Well, I would argue we possibly missed the boat a lot earlier. If you go back to basically the 1960s in New Zealand, when we had the old Department of Scientific and Industrial Research, they were looking at turning radiata pine into electrode carbon for batteries and aluminium smelting and that kind of thing. So that's basically a char making process, carbonizing radiata pine. They figured we had a lot of radiata pine growing and we could create a whole industry carbonizing that radiata pine, battery electrodes and supercapacitor electrodes and that kind of thing, and specialty activated carbons.
Yeah.
Where they've got a lot of value add in there and getting into a high-tech market. We could be doing that at a big scale in New Zealand and doing the whole value add industrial development, and you'd have biochar for agricultural applications as well. And once you've got that kind of industrial base, you've got the skills, the technologies, you've got people who know how to build the machines or repair the machines or operate the logistics, all that kind of stuff. So no, we're definitely good if we could establish something like that in New Zealand.
Yeah, I hope it's still coming. I think we might have missed the boat a couple of times in the past, but we can kind of catch up to at least make enough char for agriculture and, a bit of pollution mitigation and that kind of thing. I would love to see us become a leader in really looking after the water. I mean, I see examples where I live near Riverton. There's a petrol station across the road from a tidal water source. So twice a day, the water comes right up and it's just across the road. And so I wonder when it rains, the petrol that's leaked out and the diesel that's leaked out when people have filled up their cars that goes onto the forecourt that gets washed down is just going under a drain under the road straight into the river, straight into the estuary. I think that's not looking after the water, and I think we could be putting in there some kind of filtration bag of biochar and then periodically replacing it. And I think that should become a standard thing around all the mechanic yards, the petrol stations, anywhere else where there's a source pollution that's identifiable and kind of, to me, it's kind of obvious that it's there.
Yeah. They should have decent sumps and collection points at petrol stations these days. The older ones were probably pretty bad, but I think I had an uncle working on the concrete work, upgrading a whole lot of petrol stations. So the modern ones should have collection systems, so it's not leaching into the soil or groundwater.
Okay, so the rain then goes over the concrete forecourt, then it goes into a sump, and then does that get periodically pumped out, does it?
I'm not sure of the exact details, but I know there was a big effort probably a decade or two ago to upgrade most of the petrol stations to have better collection, runoff collection, and underground sort of catchments of concrete and tanks and that kind of thing. So it should be a lot better than it was. But yeah, then there's a lot of contaminated sites and that kind of thing that biochar could be used as part of some of the remediation there as well. Yeah,
for sure. Anything else that you would like to talk about to do with char in this chat that we haven't covered?
No, I think we've covered a range of different issues.
Yeah, I mean, I know that because you're working as a consultant with companies that you can't disclose what you're working on, so I accept that. And my curiosity, though, is quite strong to know what's happening. But are you earning the majority of your income from doing that kind of consulting work? Is there enough of that to keep you employed? And are you employed just with New Zealand companies, or are you also consulting overseas as well?
Currently, New Zealand companies could do with a bit more work in that area, but it's good to be working in that area, even if it's not full time. Yeah.
Okay. Is there a chance that you might go back to academia and do some more studies or work at a research institute?
Potentially. I thought my career trajectory would probably have been going to somewhere like Scion, one of the Crown Research Institutes. That's sort of where I saw my career trajectory going.
Okay. So you're open to it if it happens, but you're not holding your breath, and you're also basically making your own employment by consulting and that. So yeah, good on you. That's good.
Yeah.
And would you like to briefly talk about your involvement with Biochar Network New Zealand? I like to always give them a plug because it's a voluntary organization that's really trying hard to advocate for biochar. What's your role with them, John?
So I was there from the beginning, before it was Biochar Network New Zealand, and spent quite a bit of time with Trevor Richards, especially when he was traveling around the Waikato, and I was probably still a uni student for some of that time. He would get in contact with me, and sometimes I'd join him going out talking to councils or industry or farmers or whatever. So I was sort of involved from the beginning, and then Biochar Network New Zealand got set up, and it's a good organisation because it's a range of people from sort of backyard hobbyists and enthusiasts through to industry at this point, and some reasonably big industry players from a New Zealand perspective, and we sort of cater to all groups, which is good. And currently on the committee there, but been acting as a bit of an informal science advisor for a number of years with them before I ended up on the committee. So
great.
Yeah, it's a good organisation, and we need to get a bit more content out there, but in terms of some how-to guides and that kind of thing, which I'm hopeful we'll be working on over the next 6 months.
Yeah. And I'm doing some of that work as well. I just released the biochar and composting and how biochar can improve the composting process. So we've just released that as an article, and I've been sending that out to anyone and everyone that I can to get it published on websites or into magazines and things. And I'm working on one with the dairy industry. So how does biochar improve or help dairy farmers? So yeah, I'm only part-time, so it's going to come through bit by bit, but I think it's really important for us to get the information out there. And yeah, I think there's so many people in the government that probably still don't even know what biochar is. So they're not exactly going to support policies for it and investment for it if they don't even know what it is. So we just need to do from grassroots up, get the awareness out there. And yeah, so thank you for your support of BNNZ. And yeah, thank you for your time today, John. It's been really interesting and good to hear what you've been involved with in the past. And yeah, lots of good stuff. Thank you.
Yep. Thanks for having me on.
Very welcome. Okay, John, we'll keep in touch and keep up the good work.